All right, good afternoon, everyone. So today's lecture, we're going to be discussing something a little novel in our field, and that happens to be low load training or blood flow restriction. Now, some of you may or may not be aware of blood flow restriction training, but I'll go ahead and give you the nuances of it now. Blood flow restriction training is a way to still take advantage of the mechanisms that cause muscle adaptation. However, what you do is you lower the mechanical tension placed on the muscle. By doing so, um, or the way it's typically implemented is by taking elastic bands and tying them somewhat high across the limbs, such as what's being performed in this particular picture. And we'll talk about it a little bit more in its detail as we go through. Now, one thing to know about blood flow restriction training, it is a very, like I said, it's very novel, but it's also controversial. A lot of people feel like it does not actually, it's not a needed aspect for resistance training or for even athletes. But I'm going to show you guys some literature, some scientific literature to support that it actually may have benefits. Now, again, let me go ahead and clarify how it's particularly used. You take an elastic cuff and you place it high upon the limb. Now, typically, you can only do this on the legs and on the arms. Now, in this particular picture, this individual is putting them, he's using a knee wrap. The idea for practical use is you would tie that particular cuff in one centralized position at a tightness of 7 out of 10 on that particular limb. How the typical protocol would be done is you would only use about 30% of your 1RM, and your reps and set schemes would be 4 sets. First set usually is 30 repetitions. Your second, third, and fourth are 15 repetitions. And then you would only do 30 seconds of rest in between. And that is typically how blood flow restriction training is utilized. And you can use it for any such exercise such as leg press, squat, bench press, and so forth. So it does have many applications. However, many in our field feel like it is not a very good, useful technique. But it does have evidence to show that it can be used for athletes, but also for individuals in rehab, which we'll discuss in detail. So let me just give you guys an idea, right? And we've talked about this previously in other lectures. Now, this is a position stand by the American College of Sports Medicine, and it happens to talk about the practical application of load recommendations for resistance training for either athletes, just general exercise individuals, or special populations. Typically, the load recommendation is anywhere from, say, 60 to 85% of an individual's 1RM. And now, if you're a strength athlete, obviously it's going to be more. But typically, you need to be above 60% of your 1RM to see adaptations in muscular tissue. And we see that in a lot of different cases. But here are just another example of where you see increases in cross-sectional area or muscle hypertrophy based off 1RM prescriptions. So you see here, there's roughly anywhere from 60 to about 90% is where you see most changes in cross-sectional area. Same thing with the upper body. Anywhere from 60 to say 85% is where you see changes in the upper body. In addition, here's another paper by Kumar et al. In 2019, where additionally you see the molecular aspects, such as protein synthesis, is also higher at higher intensities, as such right here, from 60 to about, let's say, 85%, you see muscle protein synthesis is maximized, especially between younger and older individuals. Now, some individuals in our field have gone against the claim, and this is a perfect title: big claims for big weights with no evidence. Now, don't get me wrong, there is evidence to support that higher weights is better. And in fact, my opinion is typically you're going to use the recommended um, percentages of 1RM for exercise and also progressive resistance, such as between 60 and 85% most of the time. But there are occasions when you can veer off that prescription for special populations. For instance, if you have an athlete who is recently injured, who is coming back and can no longer handle those high intensity thresholds, but you want to have him gain similar adaptations to what you would impose. So this is where blood flow restriction training might have its best uses. However, there is some evidence to show that even for healthy individuals, it might be superior than heavy resistance training in itself. And let me give you guys an idea of those individuals who've gone against the grain. So here's one by Nicholas Bird, who happens to be a very notable researcher in our field, and he's done some great work with Cameron Mitchell and Stuart Phillips. Those individuals happen to be very big time individuals in our field. Here we have another paper by Cameron Mitchell, where resistance exercise load does not determine training-mediated hypertrophic gains in young men, which we'll cover some in a little bit. And then here's another paper by the same individual. And yet again, we have some very big individuals in our field who kind of go against the grain. And I'm going to show you the evidence to support their claims. So let's first discuss protein synthesis. Now, one thing I've mentioned to you guys throughout this whole year is that anytime that you go on to perform some kind of training, exercise or whatever, you have to look at the underlying mechanisms of what you're trying to change, right? And that has to deal with the cellular aspects. For instance, if you're an endurance athlete, ideally you're going to want to mediate PGC1 alpha, right? That's the pathway for mitochondrial biogenesis. On the other note, if you're resistance training, ideally you're going to want to initiate AKT-mTOR pathway, or another way of saying muscle protein synthesis. Now let's look at muscle protein synthesis and some differences between traditional training and also blood flow restriction. So let's just take this, and this is by Bird et al. In 2010. And if you look at the top here, what we have here is a group that trained at 90% of their 1RM to failure. Then you had another group who trained at 30% of their 1RM, but they did a weight matched group compared to this 90 fail. So the number of reps and sets that this 90% fail did, this 30% weight match did the same thing. Now we also have another group where they actually incorporated blood flow restriction. Now this group did a 30% of their 1RM, and they also went to failure. Now let's just take a look at these very closely. At rest, there's no difference in fractional synthetic rate, which happens to be, mixed fractional synthetic rate. It's just looking at protein synthesis in itself, not necessarily looking at the type. This can be either muscle protein synthesis, mitochondrial, or other different proteins inside the muscle. Now let's see what happens. So 4 hours after exercise, they do a muscle biopsy, and notably, the group that trained 90% to failure had the highest. The 30% weight matched obviously had nearly half of that of the 90. But the blood flow restriction group actually had very comparable results in terms of a mixed protein synthesis response. And surprisingly, 24 hours after the fact, the 30% actually had higher. Now, that didn't reach any statistical significance between the group, but from a practical standpoint, more is better. So who knows what the area under the curve over 24 hours might have been for the 30% blood flow restriction. Now, however, like I said before, mixed fractional synthetic rate is looking at multiple proteins. Myofibrillar fractional synthetic rate is actually looking at the muscle itself. And in this particular instance, blood flow restriction actually was the same of that of the 90% failure group. And in fact, 24 hours post-exercise, it was statistically significant over the 30% weight matched as well as the 90% to failure. So we're seeing evidence that low blood flow restriction training might actually have the same or slightly better potential increases in the cellular responses than that of a traditional training group. And yet again, that goes against the grain from what we've been told through many decades of dogmatic thinking. Now, looking at the same overall paper, though, we have to consider why that might be the case. Now, here's the thing. Obviously, when you're training 90% of your 1RM to failure, you're not going to get a lot of reps. Like in this particular instance, they only were able to get a few reps. Now, the weight match group of 30%, they're not going to get nearly as much as the volume load. And remember that volume load is a training variable that has significant impact on training adaptations. Now, here's where this may have been the case for blood flow restriction. Like I said, when you do this protocol, it's 30 repetitions followed with 30 seconds rest of 15, 15, and 15. And you see that the volume load was actually much higher than the other two conditions. Now that could explain as to why that was the case, but it's not always that simple, because I'm going to show you some literature later to show you where this actually is lower and that they still get better results or the same. Now here's a paper by Mitchell et al. Cameron Mitchell, he happens to be an astounding researcher in our field. And those of you who go into grad school will definitely get more familiar with his work. But let's just take a look at some of these figures here. In this particular research study, they had individuals train for 10 weeks. And on the very far left of this first figure here, you actually have a blood flow restriction group where they actually just trained 3 sets of blood flow restriction training. And that 3 sets was 30 reps, followed by 15, and then another 15. Then you have a group that trained 80% of their 1RM, but only 1 set. And then you had another group train 80%, but with 3 sets. Noticeably, if you look at the change in the quadricep size, the blood flow restriction and the traditional group had the same outcome. That again goes against what the typical American College of Sports Medicine position stand says about progressive increases in resistance training. Yes, indeed, you can get similar results with low load if it is blood flow restricted. And let's just look at some of these differences in changes in 1RM. Now, in this particular case, those changes were not as significant, or I'm sorry, as high as the other conditions, but they are similar. So for instance, you see roughly like maybe a 10 or maybe 15 kilogram difference in the blood flow restriction, more so even the 80% 1RM, and then probably about the same in the 80% 1RM with 3 sets. And it's pretty much universal across the board. So is there any difference between traditional and blood flow restriction? Yes, there is in terms of an application, but in the adaptations aspect, we're seeing very similar changes. Here's another look from another paper. Now, this particular paper didn't actually have blood flow restriction training, but you do see some aspects that kind of shed some light as to why it might work. So in this particular instance, this was done by Campos et al. In 2002, and here on the left it shows you the time frame and the rep schemes that each group trained at. And let's just look at the differences in changes in the muscle fiber type. Let's go ahead and look at the low rep group. If you guys can recall, type 1 is your slow twitch, type 2A is an intermediate, and type 2X is your fast twitch. I know that says B, that's an old school way of thinking. It actually should be type 2X. Type 2B is what they would consider in rats. So in this particular instance, the low rep high resistance training group actually saw increases in every aspect of that, of all muscle types. Even the same thing in the intermediate. Surprisingly, in this case, the high rep group did not see those same changes. However, those exact protocols were specific to the adaptations. So if you're training low rep with high intensities, obviously you're going to have the best increases in strength across the board. Here we see the leg press and the squat, and you're not seeing as much increases in the high rep group or the intermediate group. Keep in mind, this is not blood flow restriction. This is just traditional across the board, just looking at different intensities. But now we're going to see what happens when you actually do a blood flow restriction as we continue with some of the literature. Now, let's look at some of those things when you actually blood flow restrict in terms of strength adaptations. Here we have a study by Lorenzo et al. In 2012, where this one was done actually in 12 weeks time. Now keep in mind, this is only a leg extension exercise. But we have here 3 different groups: a light group, a light that's restricted, blood flow restricted, and then you had a high intensity group. Notice the differences between the groups. You see that the restricted group actually had the same outcomes, if not even slightly better, based off the slope of this curve, than the high group. Yet again, it goes against ACSM position stand. And we see the same thing in muscle cross-sectional area, right there. So here are some concerns about blood flow restriction training though, right, based off the literature. Most of the studies are not actually volume matched. Typically, it's either you have a low volume versus much higher volume. And like I said before, that creates some questions, well, whether it's the blood flow restriction or it's the amount of volume that they actually do. But if you guys can remember from that Campos et al. Study, they actually did much higher volume by doing 20 to 28 reps, but yet they had lower outcomes. So that might give us some indication that blood flow restriction actually has some usage. Now, usually you only train, you do one limb, or typically some of the literature shows that they do one limb blood flow restricted and the other limb is not restricted. So they're doing a kind of like a within match comparison. Typically they're only one joint exercise used, so it doesn't necessarily always have carryover to specific stuff such as squats and other big compound movements. Many, if not all, only use untrained participants, and that's a huge issue. Now the thing is, with blood flow restriction, like I said before, it has special uses for special populations, such as recently injured individuals or whatnot. Now again, it can produce improvements in muscular endurance, aerobic power, and time to exhaustion. So yet again, let's just look a little bit more closely at blood flow restriction. Typically, the types of cuff that you use are some kind of tourniquet. In science, we typically use what they call a KAATSU device, where they actually inflate a cuff close proximal to the limb, roughly, I think, about 180 millimeters of pressure. But from a practical use, you can use elastic knee wraps, or you can actually buy Velcro Velcro adjustable wraps for the arms. Now here's where it's used. Most likely used is post-operational. There's some studies to show that if individuals who are bedridden, if you apply blood flow restriction cuffs to their limbs, it actually attenuates the decrease in muscle size. So just by occluding the muscle without actually training actually helps to get it to adapt better. It has applications for rehabilitation patients or athletes, but it also might have uses for the elderly. Now here's a very, very interesting study by Cook et al. In 2014. Now many people are very weary about training athletes with blood flow restriction. One reason being is typically when you train using blood flow restriction, you're training at failure, right? You typically go to aspects of failure. And if you guys can remember me talking about training to failure, it's not necessarily the best for athletes because your rate of force development actually goes down over time. And rate of force development is the key aspect for improving athleticism, not necessarily strength. So in this particular case, this individual trained rugby athletes. Now this is an acute study, and it was only 3 weeks, and it was 3 times per week. The traditional group did a 5x5 at 70% of their 1RM, or relative 1RM. Now the BFR did the same thing, same protocol, but with intermittent blood flow restriction. It's a very good paper. If anybody's interested, they should look this paper up. But let's just look at what happens to the changes, and we're talking about percent changes, so these are pretty drastic. The dotted line here is actually the traditional group. The solid black line is the blood flow restriction. If you notice across the board in the squat and the 1RM, the blood flow restriction unanimously outperforms the traditional group in all aspects of the squat 1RM, the bench, even sprint time, as well as counter movement jump power, which was a very surprising finding, especially for an athletic population. Now it could be that this might actually have better uses for athletes. Who knows? That is very far from being elucidated. Now here we have another study with Furup et al. In 2015. Now this is also a very interesting study because he shows some key aspects as that in comparison to a regular or traditional group, blood flow restriction actually does better. And I'll give you an example. In this particular case, they had 10 untrained individuals. Both groups trained at 40% of their 1RM. Now, it was just arm curl training, but both groups trained to failure every time, right? Except the only difference is that one group had blood flow restriction. And now let's take a look at what happens. The dark bar is the blood flow restriction, and the clear bar is the traditional. Now, they recorded the number of repetitions between both groups. Now let's look what happens here. When you train blood flow restriction, look what's happening here. They actually perform a lot less reps per set. In fact, these individuals are only getting 50 or less than 50, whereas these individuals are getting roughly 150. Huge, huge difference, 3 times the amount. As we go through each set, every rep scheme is much lower in the total number of repetitions in the blood flow restriction group. Same thing under time under tension. Time under tension is lower in the blood flow restriction group. Now, based off those two things, who would you think would have better adaptations? The group that did less repetitions or the group that would do more? Typically, if they were matched, the group that did more would actually fare better. But that's not the case in this particular study. Muscle soreness, despite them doing much lower work, was greater in the blood flow restriction trained group. meaning there could be some kind of more compromisation within the muscle cytoskeleton itself, where you could be getting better adaptations. Now that might be hearsay, but for some reason they're getting better or more muscle soreness. Now let's look at muscle thickness, changes in muscle thickness. If you even look at the differences in the blood flow restriction and the traditional, blood flow restriction actually had somewhat higher than that of the traditional. Now we're looking at this in millimeters, so obviously it's not going to be that much of a greater difference, and it's not going to be statistically significant. But you're seeing that they are roughly the same across the board, despite them not doing as much work. And yet again, here's the muscle activation. You see muscle activation is much higher, again, with less work than that of the traditional group. Or the same, I'm sorry. But let's look what happens, right? Notice when they do the 3 repetition max 3RM. Is there any difference between the 2 protocols? No, there's not. However, the one difference that we did see is that this group trained 3 times as less. They only had to do a third of what this group did. Same thing with muscle volume. This one's slightly better, not statistically significant, but yet they did not have to do as much work. So yet again, it shows that by using a blood flow restriction protocol, actually might have usage for getting additional gains in maximal strength as well as cross-sectional area of the muscle. Now I believe this is the last study that we're going to cover, and this is titled The Influence of Resistance Exercise Intensity and Metabolic Stress on Anabolic Signaling and Expression of Myogenic Genes in Skeletal Muscle. And yet again, we're looking at traditional protocols in comparison to a blood flow restriction group. And what they looked at was total time under tension, the number of contractions, and the range of motion. What they also did, though, is they took muscle biopsies at 45 minutes, 10 hours, and 20 hours after exercise to see those changes occur. So here we're looking at blood lactate. Now lactate gives us an indication of their what type of metabolism is being used, right? Or what's occurring metabolically. If lactate is higher, that means they're using more carbohydrates as fuel source. Now, in some ways, that's actually better for muscle hypertrophy because that lactate actually causes a swelling effect within the muscle. It compromises the integrity of the cytoskeleton, and it causes the muscle to actually adapt by creating more muscle protein synthesis. Now, if you look at the lactate response for the blood flow restriction training group, which is this square bracket, they're actually much higher. And the reason being is because they're occluding the muscle, meaning blood is going into the muscle, but it's not coming out. And therefore, it's getting a pooling effect. And because there's not as, it's creating a low oxygen environment, they're forced to use carbohydrate to perform the exercise. Now, on the right, we're looking at AMP kinase, adenosine monophosphate kinase. That is the energy sensor of the cell. And that's something that you actually want to keep somewhat low if you are trying to get adaptations in muscle hypertrophy. Now, if we look at the high group, that response is actually somewhat high. But in the restricted group, as well as even the low group, it actually stays relatively low or even blunted to baseline amounts. Now here's where blood flow restriction actually had its benefits. If you look at that, it says ERK1 and 2. ERK1 and 2, they are what they call mitogen activated protein kinases. they work very similarly for increasing muscle protein synthesis in the cell itself. Obviously, you want those responses to be higher to increase muscle protein synthesis. And notice that it's higher than both groups across the board. So there we're seeing that certain gene expressions are actually being turned on to a greater degree using blood flow restriction. Now that basically covers a lot of the literature discussing blood flow restriction and its usage. Now I do want to summarize some things about the differences between traditional and blood flow restriction. Okay, so some important concerns is that when you do blood flow restriction, fatigue comes earlier. And that actually might be better in some cases because you can get similar adaptations with a lower amount of work. Now, here's where the thing is. There are some that promote that BFR is better. I would say that it's actually not. But it can get similar adaptations than traditional strength training with a lot less weight. And yet again, that can serve very beneficial for individuals who are injured. Now, there are very, very few studies that have done this with trained populations. There are no additional effects at higher intensities. In fact, blood flow restriction doesn't seem to work if you go beyond, say, 40% of somebody's 1RM, mainly because you can't get the metabolic stress signaling that you ideally need. Now, lastly, the mechanisms are far from being clarified. But that basically sums up blood flow restriction training. I wanted to add this particular lecture in so that you perhaps can use this as a tool for some of your athletes or even yourselves in some of your own training at specific times. Thank you.